Hi everybody, I'm Harshda Saxena and I'm an undergraduate at IIT Bombay. Today I'll be talking about using kinetic field theory, forget the long title, basically using kinetic field theory to understand nonlinear structure formation. Before I start, I would like to, of course, thank the organizers of the School Plus workshop and for having me here and allowing me to talk here. It's been an amazing learning experience so far. Secondly, I would like to thank Professor Matthias Bartelmann, under whose supervision this work has been done, and his entire group, especially Alex, Johannes, across Heidelberg and ETH. So this will be the basic outline of the talk. I'll be starting with the motivation of why Matthias started to think about kinetic field theory in the first place, what the formalism of this theory is, why we care about modified gravity, and some approximations that we'll be making to make our lives easier. So let's start with the motivation. As a lot of you already probably know, a lot of us are concerned with some large cosmology questions of how do nonlinear structures form and evolve. That is, how do things go from something as smooth as the CM, comparatively smooth as the CMB, to these rich cosmic structures that we've been seeing for a while. One of the main important questions is that, is there an analytical approach or a first principles based approach from where we can understand nonlinear structure formation? As most of you already know, we have a good idea about the linear power spectrum. We know how that works. However, when we go to the nonlinear regimes, two things start happening. One, of course, perturbation theory fails. And the second thing is a problem, what is called the shell crossing problem. So we usually model our density, our density and velocity fields of dark matter as like smooth differentiable fields. But the moment, as you've seen in simulations of dark matter halos and stuff, the velocity fields, if the streams are convergent, the velocity fields do not become uniquely valued. And that leads to a huge issue because you can't think of them as fields anymore, and that's just what is called the shell crossing problem. So this motivated Matthias to think about something called the kinetic field theory. And well, what is one thing that you know doesn't cross? And the answer to that is phase-space trajectories. So kinetic field theory is basically a statistical field theory of classical particle ensembles. Like any field theory, it contains generating a functional Z, which basically encodes all the information about our system that we want to study, and the generator fields. So the generating functional, for anybody who's done a little bit of statistical mechanics, is basically similar to the partition function. So the partition function is basically an integral over all probabilities, right? And that is what the kinetic field theory generating function also looks like. So it's basically, if you do a little bit of math, it will basically be an integral over the entire initial probability space with the inner product of the generator fields. Now, if you write the Hamiltonian of the system, you do a bunch of math, which I'll show you in a second. You will actually find out that the solution to the equations of motion looks something like inertial motion plus interactions, which is good for us. Now, kinetic field theory is something which is very, very general. I have attended multiple conferences in Heidelberg where they use this to study extremely complicated mathematical structures all the way to modeling cancerous cell growth. So this is something that you can apply to basically any statistical problem, but we'll be sticking to cosmology here. So in cosmology, we'll be moving to co-moving coordinates because life is easier. So this will be our simple Hamiltonian, and with the potential which is sourced by which follows the Poisson equation. One thing to note here is that the mass would be time dependent because you're moving in co-moving coordinates, but you also want to encode the fact that the interactions decrease. And the one way you can do that is by having a time-dependent mass. One way to, another simplification we'll be making is instead of cosmic time, we'll be using the growth factor. So we'll be changing our time coordinate. And this is basically to reproduce linear growth. So what we want to do is we want to study motion relative to linear motion. And that is what, and if you use this Hamiltonian and solve using Green's function, you end up with this very cool result, which is basically that the trajectories of the particles, this is the linear Zeldovich trajectories, and they deviate from the linear Zeldovich trajectories by this new potential, which is actually sourced by nonlinear cosmic density fluctuations. In case you're zoned out, the most important part of the entire thing is that in our formalism, the deviations from Zeldovich trajectories from initial which actually contribute to nonlinear formation is sourced itself by nonlinear density fluctuations. Now, of course, we want to study the power spectrum. And for that, we will be using what is called the number density operator, which is basically for classical particles, just the Fourier transform of the Dirac delta functions, which looks something like this. The density fluctuation power spectrum would then be the ensemble average, which also looks something like this. Now, one thing is that if you put this e to the power minus iota k dot q over, and use this q, you can see that you will have this k dot inertial terms, so this is the Zeldovich terms, which will give you the linear power spectrum. And then you'll have this exponential of these terms, which are what we really want to study, right? Because these encode the deviations from Zeldovich trajectories, which encode the nonlinear power spectrum. But here we'll be using a simplified approximation, which is called the mean field approximation. So instead of studying just this, we'll be studying the average of this, which is one approximation that we make. And if we use that, and you can see that if you plug this over here, just doing some simple math, it'll turn out that the interaction term looks something like this, where this is the one particle potential convoluted with the initial power spectrum. So this is pretty nice, right? Because we got the nonlinear power spectrum to be something which completely depends on the linear power spectrum. Just to show you that this is not all for naught, and there's actually comparisons with numerical simulations. Here we have plotted how KF, over here, it's easier to see. The normalized KFT versus numerical is pretty close to the numerical simulations until the wave number of 10 megaparsec inverse. So this is where the mean field approximation fails. Now let's go about modifying gravity. Why do we all love GR? Why do we care about modified gravity? Well, there have been multiple papers in the recent past which basically model dark energy, which basically say that you don't need to have dark energy. You can basically have a large scale modification of GR. But we all know that GR works on tiny scales, on our solar system scales, because we don't fly off cliffs and GPS works. So what you would want to do is introduce things called screening mechanisms, which basically screen the modification of gravity on low scales, so it tends to GR. Now, motivated by these modifications of gravity in scalar tensor theories, Hassani et al., a couple of folks at Cambridge, they show that using n-body simulations of spherical collapse codes, they effectively show that the major effective action of the modified gravity in these simulations is basically through a modified Poisson equation with an effective scale-dependent gravitational constant. Instead of your gravitational constant just being g, it becomes scale-dependent, which looks something of this terrible form. But the only thing to care about is that you can model multiple screening mechanisms, and you have now a scale dependence in your effective gravitational constant, where k star is basically a transition wave number, which basically denotes at what wave number your screening starts to activate. So it basically goes from modified gravity to GR. And this is how the simulations look like. Now our work is easy because we just need to plug, as a first approximation, what we'll be doing is we'll be fixing our growth factor to the GR limit. I will modify this approximation in a while. But what we all need to do is we can just plug in this G effective in our KFT theory and then see what the interaction term looks like. So the interaction term looks something like this. This is just the convolution. I know it looks ugly, but it's not that hard. So the good thing about this is that as long as you can parameterize a modified gravity theory in some form and give that to me as a scale-dependent gravitational constant, I can plug it into the interaction term and give you the nonlinear power spectrum up until, of course, the mean field approximation is valid. So this is what the modified power spectrum looks like versus GR. So here we have plotted for NDGP models. So that's specific modified gravity models with Einstein screening. And you can see that for low K star, which basically means for all your analysis, all your wave numbers are much greater than your transition wave number, which basically means you're in the GR limit. You have low amplitudes of the relative power spectrum, as we expect. But for higher, you do have a higher amplitude of your relative power spectrum along with deviations in the peak. Now, one way which you can also make our life easier is using Taylor approximations. So we usually expect tiny perturbations around GR, if modified gravity is indeed correct. So we can express the nonlinear power spectrum, since we have a functional form of that, as a Taylor expansion around GR. So since we've just modified the effective gravitational constant, we can represent it in terms of this functional derivative of the power spectrum. And this is good because then we just need to evaluate once at GR. And then again, you can just give me any modified gravity model, parameterize it in terms of a scale-dependent effective gravitational constant, and I can give you the Taylor approximated nonlinear power spectrum. So just to see what this functional derivative actually looks like, this is a plot over here. So it's basically models the change of the interaction term at some given k and a at some wave number with some perturbance introduced at some alpha and x. So you see that there's no sort of weird coupling of modes. So if I introduce a perturbation at, if I want to study the change of the interaction term at k equal to 1, the maximum things which matter are the perturbance at also introduced in gravity also at k equal to 1. Another thing is if I introduce the perturbation way too early, of course, the growth is just linear. So the interaction terms don't change a lot. So there's not a lot of change in the non-linear path spectrum. And if I introduce it too late, these perturbations don't have enough time to settle in and actually modify the path spectrum. So it looks something like this. So just to show, this is the path spectrum. This is the functional derivative. It's ugly, but it's doable. So this is just to show for some modified gravity models that the Taylor expansion approximate pretty close, is very close to the exact thing that we found over here. So just this path spectrum, and this is the exact formalism. So the Taylor expansion works pretty well. Of course, I've cheated a little bit over here and seen only like tiny deviations from GR. But even in that case, for NDGP with Weinstein screening and for FFR with camouflage, Yukawa, and chameleon screenings, you can do this for, as I said, you can do this for any modified gravity model as long as you have some, effective parameterization. So you can do this and you see that it works pretty well. And basically the thing is, again, in case you zoned out, with a modified gravity, we expect enhancement of the power spectrum on intermediate scales. So some things that we're still working on is, I think a bunch of people talked about this before, is we had as a first approximation fixed our growth factor, but what if we don't do that? Well, the exact case becomes slightly complicated, but it's easy to do in the Taylor expansion term where we just have to introduce an extra functional derivative, which has already been solved by Alex using the growth equation. Another thing is if you change the power spectrum, you will realize that, which other people have already seen, the amplitude of the power spectrum changes, the relative shift changes, the shape changes. So we need to also take care of that by appropriate corrected amplitude of this form, which changes the shape. Another thing which would be most relevant for everybody is to compare with observations and derive constraints and modified gravity models or from the expected and observed spectra. So I'll just put my summary slide here and thank you.
So we can have a couple of questions.
It's okay. This is a very interesting approach, but I don't understand something fundamental. So the theoretical framework itself is in Lagrangian space. Is that correct? That you are talking about trajectories.
Yeah.
So then how do you deal with things like force softening, which simulations do in order to, in order to account for the fact that the sampling of phase space is not by actual dark matter particles, but by these pseudo n-body particles, and that these particles should not have strong interactions, strong gravitational interactions at small distances.
Right. So that's another thing, which is one thing which I was actually wanted to mention was that KFT is actually, we're just modeling lambda c. We're just modeling dark matter for this moment. So we're not.
Yes, but this is about dark matter.
Okay.
It's the dark matter fluid, which your n-body simulation approximates as a bunch of n-body particles.
Right.
And these particles should move through each other. They should not do two-body scatterings because of the 1 over r squared force.
Right. So that's, but then that problem doesn't come in because we're only worried about phase-space trajectory, right? So they won't cross. This is what I showed.
No, the particles are still interacting by gravity.
Yes, they are. And that's what.
So they interact with 1 over r squared.
Right.
And they should not.
Okay.
If you are going to compare to trajectories with n-body particles, maybe I'm missing something.
Yeah,
basic.
we can have a talk later.
You can discuss this during lunch. So, so next, anybody has questions? Okay, sorry.
So even within lambda CTM, are there efforts within this framework to improve the agreement with the n-body? Because you have 10% differences at k of 0.1.
Right.
And to really make or to do cosmology, you want that to be slightly better at those cases, no?
Right. So what they have done is what we're currently working on at Matthias's group is this mean field approximation. So this actually messes a lot of things up because you replace this by just the average, which loses a lot of the information that we don't want. So we've been trying to work with this mean field approximation. That's a current thing in progress about. And we have actually preliminary results, which I don't have over here right now, that if you improve the mean field approximation, this becomes slightly over here, so that it becomes better.
So thank you, Harshda. It was a beautiful talk.